Chapter 2 of your textbook is where we really get started talking about biomedical signals or biosignals. And we're going to make a lot of definitions and talk about some terminology, some of which was alluded to in the first two lectures. We're going to get more in detail with this material so that you have a better understanding of how we talk about signals. So, basically, signals can be classified into two major subgroups, and we're talking here about digital signals because we assume that by the time we get to working with the signal in signal processing, it's been acquired and converted from analog to digital form and probably stored in memory, with the exception of occasionally working with real-time signals. So digital signals can be classified into major subgroups. The first classification is whether they are linear or nonlinear. So linear signals differ from linear processes, or come from linear processes, while nonlinear signals arise from nonlinear processes, such as chaotic or turbulent systems. Nature is inherently nonlinear, and almost all of the systems in the human body are chaotically driven. Even things like the heartbeat actually has a clear element of chaos in it. And there's turbulence from everything from blood flow to fluid flow within the body. So, however, what we can usually do is we can usually work within a linear range. So we can take nonlinear systems and treat them like they're linear if they can either be approximated as linear or if there's some range over which they're linear. Now, there's an additional classification called stationary and non-stationary. And basically, a stationary signal is going to have statistical properties that don't vary over the data set being analyzed. A non-stationary signal will have statistical properties that can vary. In electrical engineering, we often put a little more rigorous definition on this and say that basically a stationary signal will have, in addition to consistent statistical properties, we will say it has a consistent frequency spectrum. So whatever analytical tools we apply really depend on the signal that's being used. So initially we'll look at linear stationary or linear time invariant systems. So here's just a flowchart that represents the way the signals are divided and looks a little bit at how your textbook lays out the discussion of such signals. So the first and probably majority of the class will be discussing stationary signals. We will not discuss two-dimensional signals in this class. So we're not going to do image analysis in this class because there are a number of courses that you can take within the department that work with both image analysis and medical imaging and related topics. So we're primarily talking about time domain signals, one-dimensional signals in this class. So the bulk of the course is devoted to stationary linear systems. So what is encoding? Well, all signals involve some kind of encoding scheme, and you can divide that into two broad categories, continuous or discrete. Continuous signals usually encode information in terms of signal amplitude as a function of time. So if we're making a measurement of, say, heart rate as a function of time, what we're actually looking at is a graph of voltage as a function of time, and so that's considered encoding. The temperature in a room can be encoded so that 0 volts represents 0 degrees C, 5 volts represents 10 degrees C, and so on. And so if this is linear, then we could write an equation that relates voltage amplitude to temperature. So when the input is related to the output through an offset and a slope, we say we have a linear signal. So this is the old equation of a straight line that you learned way back in algebra. Y is mx plus b, where m is the slope of input-output and b is the offset, which in our temperature example could be 0, but doesn't have to be 0. So the temperature can be found from the voltage output by solving the equation or inverting the equation. When the information is encoded in terms of a signal amplitude, it's known as an analog signal. The concept of linearity. So linearity has a rigorous definition. But basically, linearity means proportionality. So in other words, if you double the input into a linear system, you will double the output. Another way of stating it is to say the whole is equal to the sum of the parts. Another way of stating proportionality mathematically is to say if an independent variables of a linear function are multiplied by a constant k, then the output of the function is also multiplied by k. And so that would be this relationship here at the bottom of the page. So k, the constant, just comes out of the function if the function is linear. Some of the properties of linear systems, if we take the value of a function at x1 and the value of a function at x2 and add them together, that's the same as if we took x1 plus x2 and evaluated the function there. If some term z is equal to the first derivative of f with respect to x, and then that's multiplied by a constant k, we can pull k out of the derivative function and basically treat it as just a multiplier. So the constant has no impact on the derivative of the function. Same is true for the integral. So derivation and integration are linear operations. Systems that contain derivative and integral operators and other linear operators produce linear systems. So linear system theory or analysis can be applied when you have linear functions, derivatives, and integrals. So analog encoding used to be fairly common in consumer electronics. Most of these applications now use digital encoding. And then there is this comment, the strange resurgence of vinyl records is a notable exception. And I noticed when I was Christmas shopping this year that apparently everywhere now we have the turntables on sale. That was kind of the hot item this Christmas because people seem to think that the vinyl records are better in sound quality. And then I saw this funny cartoon on Facebook that said the reason that we thought vinyl records sounded better was the music was better. Anyway, whether that's true or not, I don't know, but I thought it was funny. So analog encoding is important to the biomedical engineer because most of your transducers generate analog encoded signals. This is changing. Some EEG systems now, the transducer itself obviously measures the signal, an analog signal, but within the transducer, you sometimes have the A to D conversion done in the transducer. And so what actually comes out of the transducer now is a digital signal. In this book, it's assumed that digital signals are digitally encoded, usually from an analog source. And we talked about how this is done in Chapter 1. Basically, when you change an analog signal to a digital signal, you're doing two things. You're, first of all, allowing it to occupy only discrete levels in amplitude, and then you're sampling it at specific times. So digital signals basically give you a function that is given at specific points in time. It's usually stored in some kind of sequential memory location. In MATLAB, we tend to store this kind of data set as an array. The memory index number n relates to the time associated with a given sample from the sampling time or the sampling frequency. So if we know our sampling frequency, and we can then take our index n and convert that to time. This is important because when you do calculations in MATLAB, it's going to automatically revert to showing your whatever you're calculating as a function of index number. So unless you manually go in and give it a time scale and ask it to plot as a function of time, you won't get a plot as a function of time. You'll get it as a function of index number. So what is time invariance? That's another really important concept. Time invariance says that if a signal's response characteristics don't change over time, in other words, its statistical properties are constant, it's said to be time invariant. So this is a stricter version of stationarity. So mathematically, if f is a linear function, then for time invariance, the f of x of t minus t is equal to y of t minus t. So for time invariant signals, you don't want to include this with time varying, okay? So signals that fluctuate in amplitude. T here is the, so signals can be time invariant but still be time varying. So what you're looking at is what is it that's time invariant? It's the statistical properties. So a system that's both linear and time invariant is referred to as a linear time invariant or LTI system. And an LTI system, many of you have had some signal processing classes where maybe you've used Fourier analysis, maybe you've used Laplace analysis. All of those techniques assume linear time invariance. And so we have a lot of techniques or tools that we can use when we have a linear time invariant system. So almost no actual human or animal or even plant systems are linear or time invariant. In fact, one of the reasons we manage to stay alive is that we are highly adaptive as a system. So our properties do change as a function of time. One of the assumptions that we can make is, first of all, as we said before, that we can work over a limited range and assume our system is linear over that range. And the other thing we can do is we can work for a short period of time. So if I acquire your brainwaves for 2 seconds, I can assume some degree of stationarity of your signal as opposed to if I try to do that over 24 hours. So the last thing to talk about in this little sequence of definitions is causality. So a system that only responds to current and past inputs is causal. And all systems that exist in the real world have to be causal. So you can't have a response to future values. You can only have a response to current and past values. Now, the computer actually doesn't have to do this. So the computer can operate, because you have things stored in the computer, it can operate using future values because they're stored in a data file. And so when you use that, that's basically a non-causal system. And this is splitting hairs a little bit, but basically, whether it's causal or non-causal, the practical implication has to do with kinds of digital filters that you implement. All right, so linearity is required for the application of a really important concept known as superposition. Superposition says if you have 2 or more inputs that act on a linear system, the system responds to each one as if it were the only input. And so the output is the sum of the response to all the inputs. So we say this allows a divide and conquer approach where really complicated stimuli can be broken down into simpler components, and you can do an input-output analysis on each subcomponent like the others didn't exist. Okay, so here are some basic signal measurements, some definitions, and we mentioned some of these terms in Chapter 1. So one important thing, and notice here these formulas come as 2 different kinds of formulas. One is if we have a continuous system. So in a continuous system, we would have some equation that would define our function. And so if you want the mean or the average of a continuous value, you would integrate that value over a period and then divide by the period after you've done the integration. If you have a set of discrete values, then basically you take the sum of all those discrete values and divide by the number of values. And so this gives you the mean or the average value. The RMS value is basically you take the function and square it and then do the same sum, divide by the number of points, and then take the square root. So what RMS gives you, if you think, for example, so here's the RMS formula for discrete, here it is for continuous. What RMS gives you, it gives you sort of an effective constant energy. So if we were to think in terms of electrical engineering, for example, and you have all these time varying signals, um, let's say you have a simple sine wave. So if you have a simple sine wave, which is centered around the origin, if you were to take the mean of that, you'd get 0. But yet we know from the fact that AC current powers our world that in fact you're pulling power from that. So what an RMS value gives you, sort of an analogy, is it gives you the effective DC current that would generate that same power level. And so for a sinusoid, that's just the magnitude of the sine wave over the square root of 2. For a more complicated signal, we go basically to the formulas for RMS. So here's an example of finding the RMS value of a sinusoid. Basically, when you take the sine squared, so your x of t is some amplitude times the sine of omega t, where omega can be found as 2 pi over the period. We take that, we square it, we use some trig identities, and basically from the trig identities, when we do the evaluation of that, we get 0.707 times the amplitude, or the amplitude over the square root of 2. So I'll let you kind of go back and look at that. What I've always done, this is a little bit different. I've always done this with a cosine function, and then there's kind of a convenient. The cosine of x squared is 1/2 plus 1/2 cosine 2x. I think the cosine of sine squared is 1/2 minus 1/2 cosine. Don't quite remember, but there is a trig identity that you can use for that. Then allows you, by the fact that you're integrating over a full period, and that over a full period the integral of a simple sine function is 0, and then you have a constant that integrates and gives you your square root of 2. So that's maybe a little bit easier to use that formula. So this is the analytical approach. If we wanted to do a computational or a digital approach, basically what we have to do is we have to generate a sample sine wave. So in this example MATLAB code, you're given a sampling time of 0.005 seconds, 500 points, and so you set up your sine wave here using frequency and time. You have to set up a time array. Time runs from 1 to n, and then you multiply that by the sampling time so that you get that in seconds. Then you use the RMS formula basically by taking the mean of x squared and take the square root of that. So I think it's a really good idea if you don't have any experience working with MATLAB, if when we come across some of these codes in our lectures and in our textbook, basically just open up MATLAB and start to type in these commands. And then you'll see what each command line does. And sometimes I would even, not always because sometimes you get a lot of stuff back, but sometimes I even leave off the semicolon so that you can see what MATLAB generates with each step. And so in this case, if you do that, you're going to get 500-point arrays for things like your time and your sine wave. But sometimes it's interesting to do it once if you've never worked with this before, so that you actually can physically see what's coming out of your calculation. Okay, another couple of basic signal statistics. The variance sigma squared is given by the definitions shown below, and it's a measure of signal variability that's similar to RMS. And the standard deviation sigma is the square root of variance. Probably you've heard more about sigma than about sigma squared. So in MATLAB, there are some commands: mean, variance, and standard deviation. And so if you have a vector that you've defined as x, so like a number of variables, and that's a row vector, then when you take the mean of x, you get the mean of each column. And the same is true for standard deviation and variance. So you can have multiple channels or multiple measurements, and you can take the mean of each one all at the same time if that's represented as an array in MATLAB. So this is an interesting example. Basically, the example here is to evaluate a signal to determine if it's stationary. And if it's not, to try to modify the signal to remove the non-stationarity if possible. So along with this textbook, you have a series of files that come associated with the book, either by download if you buy the electronic version, or by DVD if you buy the book version. So in part one, we just want to determine if the signal is stationary. There are lots of different ways to do this. One possibility is just to segment the data into a number of segments and then look at the mean and variance and see if they're the same everywhere. And there's no clear guideline for what the length of the segment should be, but it should be reasonable. So for example, let's suppose I'm looking at your heartbeat and I want to determine if that's stationary. It wouldn't make any sense to have time segments to compare that were, say, milliseconds, because your heart beats once every second. So if I wanted to determine if that was stationary, I'd probably divide that into 10-second segments, because that's just kind of representative of the real world. Okay, here's the code, basically loading the data, dividing the data into 4 segments. Here's how we create the segments. So we actually run our segment from some point to that point plus 249. Here's taking the average of the segment. Here's taking the variance of the segment. And then here's displaying the output. So here you can see the segments and the mean and the variance. And you see that the mean is quite a bit different, but the variance is sort of close to the same. So a couple of different options. One thing you can do is you can take the derivative of the signal. And when you take the derivative of the signal, then basically that tends to do away with things like long-term or DC drift. And so these slowly varying changes when you take the derivative look like 0. So that's one trick. Another trick is to detrend the data, which we'll discuss in a later chapter. So here's where we take the derivative of the signal, and then once the derivative is taken, once again resegment and compare, and you can see that you have some basically means close to 0, so you're a little closer to stationary. The variance is also pretty small. So by doing that, so sometimes this is referred to as the transformation of data or the transformation of a signal, not in the quote-unquote transform like a Fourier transform, but it is transforming the data into a different form. And so taking the derivative sometimes will improve the stationarity of the signal. So that concludes this portion of this lecture, and we'll have a second and third lecture on chapter 2 also posted.